Good afternoon, everyone, and welcome to the II-CC webinar series. Today we have Dr. Zhiqiang Mao from Penn State University. Dr. Mao works heavily on bulk crystal growth, and today I'll be talking about layered magnetic topological materials, and he is the lead for bulk crystal growth in the II-CC. Dr. Mao, please go ahead.
Okay, good afternoon, everybody. So today I'm going to talk about our study on layered magnetic topological materials in MnBi2Te family. So I have not only show my our in-house work, I also at the end mention some work done by user on this material family. So before I start, I want to thank my collaborators. So the most of the work which I'm going to show mostly done by San Li, Yanglin Zhu, who has already left, and my graduate student Yingdong Guan, and Yuan also made important contribution to some of the work. And this work done involves many collaborations. For RPAS measurement, we collaborate with He Mian, Nitin, Trezu, and also some measurement done at UC Berkeley with Lonzero. And also we did the high field measurement at the National High Magnetic Field Lab in collaboration with Graf and Choi. For structure study in TEM, we collaborate with Leishing and Nothing. Okay, so here's the outline of my talk. First, I will give a brief introduction to quantum anomalous Hall effect and the intrinsic antiferromagnetic topology insulator MnBi2Te. That is a new platform to realize quantum anomalous Hall insulator. Then I'm going to discuss two topics. One is ideal ferromagnetic type II Weyl semimetal state, which we demonstrated in antimony doped MnBi2Te. The other topic is the tuning of magnetism carrier type concentration in the heterostructure compound. MnBi2Te integrated by Bi2Te. So most of the results I'm going to present already published or included in the submitted manuscript listed here. So now let me tell you what is a quantum anomalous Hall insulator. And so the quantum anomalous Hall insulator is characterized by a quantized Hall resistivity at the zero field, as shown in this schematic, and zero longitudinal resistivity. So what happens to this state is that at edge it has a spin polarized ballistic chiral edge mode. So this edge mode can support dissipation of this current. So such a state can be realized in topological insulator with ferromagnetism. So what happens is the following: in topological insulator, it has a gapless Dirac surface, Dirac cone state. But in presence of ferromagnetism, it breaks time reversal. So open the gap and the chiral edge state will be present as shown in this schematic. So the first the observation of quantum anomalous Hall effect is in chromium doped bismuth antimony telluride films. This work was done by Trezu, my colleague, and together with his collaborators. So they demonstrate zero field Hall resistivity quantization as shown here. And recently, such a quantum state also observed in other material systems, including twisted bilayer graphene and MnO2, WT2, Moray heterostructures. These are recent works such here just mentioned. I'm not showing you the detailed results. But the problems with the current material systems is that the required temperatures for observing quantum anomalous Hall effect is lower, either in sub-Kelvin range or below 3 or 4 Kelvin. So the one of the focus of direction in this field is to look for materials which can realize quantum anomalous Hall effect at a higher temperature. So theoretical studies suggested topological material with intrinsic magnetism can possibly host high temperature quantum anomalous Hall insulator. So there have been a lot of theoretical effort which predict intrinsic magnetic topological material. So MnBi2Te is the first established intrinsic antiferromagnetic topological insulator. Here I'm showing the structure. So this structure actually evolved from bismuth telluride. So it can be viewed as intercalation of manganese tellurium into the Bi2Te quantable layer, forming such a septuple layer. The compound still preserve the non-trivial band topology that is generated by inverted bismuth and tellurium PZ bands. So that creates a topological surface state. But intercalated the manganese carry magnetic moment. It orders ferromagnetically within a septuple layer, but this ferromagnetic layer stacked antiferromagnetically along the c-axis. So the ordering temperature is 25 Kelvin. So both band structure calculation and RPAS, demonstrated. This is demonstrated. This is a topological insulator, and the magnetic ordering also, probed in magnetic measurement as well as in neutron scattering. So it is intrinsic antiferromagnetic topological insulator. And theory further predict if this material can be reduced to 2D thin layers, it could realize new topological quantum state, including quantum anomalous Hall insulator and axion insulator. So if it's reduced to the odd number of septuple layer, it can realize a quantum anomalous Hall insulator as shown here. So in this state, the both top and the bottom surface can have quantized Hall conductance, and they have the same sign, so they will add up together. So you can have a quantized Hall conductivity, but in films with odd number, even number of septuple layer, and then the Hall conductivity in top and the bottom surface would have opposite sign, so they cancel out. So the Hall conductivity would be 0 now. So chain number would be 0 now. And then these predictions has already been. Sorry, I don't know how it's frozen. I cannot switch to next slides. Okay, now it's working. Okay, so this prediction has already been demonstrated in experiments of both quantum anomalous Hall state and the axion insulated state has been observed. So this work is done by Yuanbo Zhang at the Fudan University. The close quantization at zero field is observed. And the axion insulator work is reported in this work. And also here I want to mention, so this materials also can show another very interesting quantum phenomena called the layer Hall effect. This is a more recent work published in 21. I want to give a little bit more explanation about that. So basically in axion insulating state, the top and the bottom surface of the film show layer locked barrier curvature, meaning barrier curvature at the bottom top surface has opposite sign as shown here. So if electric field is applied, the electron will be deflected, by anomalous velocity. But however, without the vertical electric field, the positive barrier curvature, negative curvature from top and the bottom layer are degenerated. So it doesn't show a anomalous Hall effect. But if you apply a vertical electric field here, that lifts the degeneracy of barrier curvature. And then it could show the anomalous Hall effect. So basically the applied vertical field can turn on the anomalous Hall effect. So that's the key evidence of layer Hall effect. And another interesting phenomena in the system is the coexistence of a quantum anomalous Hall and the quantum Hall effect. So this is a theoretical prediction. So at the zero field, disorder can localize the bulk state and forming chain number 1 quantum anomalous Hall state. So this is a predicted phase diagram. And such a coexistence of quantum anomalous Hall and the quantum Hall has already been demonstrated in experiments. So this is a recent experiment results. So the quantum Hall state with C equal to 1, and the coexistence of quantum Hall and the quantum anomalous Hall with C equal to 2 and 3, all resolved in experiment. So here's a phase diagram, as function of carrier density and the field. The quantum Hall state, quantum anomalous Hall state is present in the canted antiferromagnetic phase. And when the at higher field, and then you can see higher chain number phase, which include both quantum Hall state and the quantum anomalous Hall state. Theory also predict this system could show a topological phase transition from antiferromagnetic topology insulator to Weyl semimetal in bulk. So because interlayer coupling is antiferromagnetic, and this coupling is not very strong, so if we apply field along z-axis, the magnetic state can be polarized to ferromagnetic as shown here, and this would cause a band structure transition. So in antiferromagnetic state, it is a topological insulator as I just described, but in ferromagnetic state, the ferromagnetic exchange interaction will cause band splitting and crossing, so forming a type II Weyl state as shown here. So we would expect to such a topological phase transition driven by magnetic field. However, in pristine MnBi2Te, there is no evidence observed that. We observed such a state by tuning antimony concentration in this MnBi2Te alloy. The reason is that in pristine MnBi2Te, the Weyl node is not close to the Fermi level. It's heavily doped for pristine MnBi2Te, as shown here. So it's a large electron pocket, and Weyl node is far below the Fermi level. So in transport measurement, we cannot see it in ferromagnetic phase. So to observe that, we need to move Fermi level to the Weyl nodes, right, as shown here. So we need to reduce the electron doping. Actually, the Weyl node is close to Fermi level at a slightly Hall doping now. So at that point, and then the Fermi surface include a small Hall pocket coexisting with 2 point-like electron pocket. So we can observe the predicted ideal Weyl state only at such a the state. So this is what we demonstrated. Okay, so now let me show you our work. So we first studied the MnBi2Te. Our crystal was grown using the flux method. And first we did the structure study. We first demonstrated that the structure of this compound is indeed formed from the stacking of MnBi2Te septopole layer. So this is a TEM image. And in ferromagnetic measurement, we also found it has a spin flop phase, meaning canted antiferromagnetic phase between antiferromagnetic and the ferromagnetic phase. The field range for this phase, the spin flop phase, is from 3.5 to 7.7 Tesla now. And we also did the transport measurement. We found such a canted antiferromagnetic phase. The features anomalous Hall resistivity. You see the hump in Hall resistivity. By subtracting normal Hall resistivity, we can extract anomalous by subtracting the conventional Hall contribution, and when we can extract a normal Hall resistivity. And then we plot it as function of magnetization, so we can see it is not a linear dependence, right? So it's a show, there's a curved shape, so that indicates this normal Hall resistivity has intrinsic origin, meaning driven by barrier curvature. So when we convert it to a normal Hall resistivity to a normal Hall conductivity, you see a peak here. So this peak coming is driven by the barrier curvature. So that was previously predicted by theory. As long as the spin structure is non-collinear, it could generate intrinsic anomalous Hall effect. Then, as I said, to observe the Weyl node, we have to tune chemical potential to close to Weyl nodes. So we did fine tuning by antimony substitution for bismuth. So here is our results. This shows you the carrier density and the mobility as function of antimony concentration. So we found that when antimony concentrations are around 26%, the carrier density is minimized, reduced by 2 orders of magnitude compared to pristine compound. And the mobility is significantly enhanced. So our theory collaborator Yuanxi Wang, did the calculation. Yeah, his calculation suggested around 26% of antimony Weyl nodes supposed to be close to the Fermi level in the ferromagnetic phase. So we indeed observed transport evidence in this in sample close to this concentration, 26% antimony. So what I'm showing here is the RPAS data measured on sample with lightly electron and Hall doping. So the transport signature of Weyl state is observed in lightly Hall doped sample. So here the Fermi level pretty close to the top of the conduction band, clearly is Hall doped. So now let me show you the transport evidence. First, let's look at the Hall resistivity. So here we also put it together with the magnetization data. So the blue curve is magnetization. That can tell us the phase transition from AFM to canted AFM to ferromagnetic. So that's labeled with a different color. If we look at the data measured at a high temperature in paramagnetic state, so we don't see any transition. It's a smooth curve. But when we reduce the temperature below the magnetic ordering temperature, which is 24 Kelvin, we found the Hall resistivity is suppressed, right? And also at the spin flip transition field HC2, we see discontinuous change at the magnetic phase boundary. So if we plot the Hall resistivity at 20 Tesla, we can see how it's suppressed, right? And this suppression of Hall resistivity is sharply contrasted with the data measured in heavily Hall doped or heavily electron doped sample, where we don't see any suppression. Field when we go from paramagnetic state to ferromagnetic state, there is no change. But in the light Hall doped sample, it has a suppression. So this suppression of Hall resistivity can be understood in terms of the expected the electronic structure transition. So in paramagnetic state, it's Hall doped. It should only have one small Hall pocket. But when it enters ferromagnetic state, because it's the Fermi level close to Weyl node, the Fermi surface should have the two components, one Hall pocket coexisting with 2 point-like electron pocket, which I just described in this schematic. So, in transport, Weyl state has 2 remarkable signature. One is QAHI anomaly. The other is a large anomalous Hall effect. So first, let me show you the evidence of QAHI anomaly. So what a QAHI anomaly means is when you apply magnetic field parallel to electric field, the resistance of the sample should decreases, meaning negative magnetic resistance. And that is driven by a topological effect called the topological current. So we measured, to demonstrate that effect, we measured 4 samples. We measured the C-axis longitudinal magnetoresistivity. So we selected 2 lightly doped samples. E2 is a lightly electron doped. H1 is the lightly Hall doped. E1 is a pristine compound, heavily electron doped. H2 is heavily Hall doped. Now let's compare their C-axis longitudinal resistivity. So in pristine compound E1, we observe the spin valve effect when we go from antiferromagnetic state to canted antiferromagnetic state, we see suppression in resistivity. So that is caused by suppression of spin scattering called spin Weyl effect. And this effect becomes much more significant in light electron doped. So we see stabilizer drop. The drop could reach close to 90% at the spin flipped transition field HC2. So this typical spin Weyl effect. And in heavily Hall doped sample, we see similar behavior. But the lightly Hall doped sample behave very differently. First of all, in the canted state, doesn't show step-like drop, and also in above HC2, it continues to decreases with speed. That sharply contrasts with other samples where resistivity gradually increases above HC2. So that implies we may have a QAHI anomaly effect, but this is not sufficient. So we need to look at their angular dependence. For QAHI anomaly effect, the decrease of resistance is caused by chiral current, which is proportional to this dot product. E is electric field, B is magnetic field. So from that, you can tell when we rotate the magnetic field away from the electric field, and this dot product will become smaller. And so the meaning negative magnetic resistance should become smaller, and at some angle, it should become positive. So we indeed observe such angular dependence. So magnetic resistance change from negative to positive. It becomes positive above 50 degrees. However, for those samples showing spin Weyl effect, you can see above HC2 they show very weak field dependence. So this gives us strong evidence for the QAHI anomaly effect. So now let me show the second evidence of large intrinsic anomalous Hall effect. That's a typical signature of a Weyl state. So the data shown here is moderate Hall doped sample, Hall resistivity at different temperature. So this is a field. And we first need to subtract the normal Hall contribution. So linear background is from the normal Hall contribution. And then we extract the normal Hall resistivity, and using this equation to convert normal Hall resistivity to normal Hall conductivity. So in the ferromagnetic state, the maximum value reach 42, which is pretty close to the theoretical predicted value. So for ideal Weyl state, a normal Hall conductivity can be estimated using this equation. Delta K represents the separation between the two Weyl nodes. So the estimated value is 35. It's comparable to our experimental measured value. And we also converted a normal Hall conductivity to Hall angle. So we found near Hall, lightly Hall doped sample, Hall angle could reach about 10%. So that's the signature of a Weyl state, once as I just mentioned earlier. And recently, we also observed the thermal transport evidence of the field-induced Weyl state. So we did the thermal conductivity measurements. So what I'm showing here is the whole magneto thermal conductivity for MnBi2Te and MnBi2Te with x equal to 0.26. So now first let's look at data of a MnBi2Te parent compound. So there is a large suppression in the spin flop phase. This is because in this field range, there is a very strong phonon-magnon scattering that is revealed in previously reported work. So that's already understood. Above HC2, the phonon band does not overlap with the magnon band, so the overlap becomes smaller. So that thermal conductivity increases. So meaning phonon thermal conductivity increases. And now let's look at the data of MnBi2Te, which show Weyl state, right? And we have electronic structure transition. We have a Weyl fermions above HC2 that should contribute to thermal conductivity. So compared to MBT, MBST show positive magnetothermal conductivity. For MBT, you know, it's negative magnetothermal conductivity. So we have significant enhancement. So, you know, when we rotate field to in-plane interaction, we don't see that enhancement because in-plane field does not generate a Weyl state. And this also supported by this claim is supported by the data measured in paramagnetic state. So in paramagnetic MBST does not show, the data does not show field orientation dependence. And also the thermal conductivity MBS is smaller, even smaller than MBT is opposite, right? Because in paramagnetic we don't have a Weyl state, so that's why. But the MBST has more disorder that reduce thermal conductivity. That's why it's less. Okay, and then we also did seeback coefficient measurement as function of temperature on the different fields. So here we'll put this data together with the magnetic phase diagram. So when field is below spin flop field, which is 3.5, so if you look at data 3 Tesla, 1 Tesla, they show linear decreases. And then they don't show the transition at the magnetic phase boundary because carrier density is very low in the system. However, when field is above the spin flop field, 5, 7, 8, 9, 7, 9 is already in ferromagnetic state. We see the large deviations from the linear theta, right? So in the ferromagnetic state. So this very consistent with the electronic structure transition from paramagnetic state to ferromagnetic state, which I described earlier, right? In paramagnetic state, we have a small hole pocket. In the ferromagnetic state, you know, well known close to Fermi level, and the Fermi surface has two components, one hole pocket and 2 point-like electron pocket. So this suppression of seeback coefficient is due to presence of this electron pocket, because electron pocket should give rise to a negative thermal the seeback coefficient. So that's why, but the contribution is small because the Fermi surface of electron pocket is small. Contribution is small. That's what explains this deviation. Okay, and now we all. So how much time I have? Okay, then I'll continue now. And we also did high field measurement for transport, and we observed for lightly doped sample, we observe quantum oscillation. This is an electron doped sample. So the quantum oscillation is present above the spin flip field, HC2. After subtracting background, we can see a very striking oscillation. By doing Fourier transform, we can extract quantum oscillation frequency. We found a quantum oscillation frequency is temperature dependent. So you see it becomes larger below ordering temperature 24 Kelvin. So that indicates the electronic structure couples to the magnetism. Yeah, because you know when it becomes ferromagnetic, they should lead to the band splitting now. So Fermi surface should change that. And we also observed this in a lightly hold of the sample now. For lightly electron doped sample, Fermi the Weyl node still away from the Fermi level, so we cannot see the Weyl Fermion transport behavior. And then we did this measurement on a group of sample. So here I'll show you how the quantum oscillation frequency vary with the doping level. So if we add more Hall carrier, density becomes the oscillation frequency becomes larger, and more electron doping also leads to larger doping. So we observe the Weyl state in this sample, the lightly Hall doped. So because the Fermi surface is is very small, right? 1 Hall pocket, 2 electron pocket. This oscillation frequency should come from this small Hall pocket, right? So this is data fully consistent with what the band structure evolution as I just discussed. So next, I move on to next topic, the MBD heterostructure. So this system allows the tuning of magnetism, and also we can tune carrier type and carrier concentration. And this system is also a platform for seeking a variety of topological state, including quantum anomalous Hall, axion, high order TI, and so on. So this heterostructure compound is formed by intercalating bismuth telluride quintuple layer in between MnBi2Te4 layer. If we only intercalate single layer, quadruple layer, it forms this phase 147. If bilayer bilayer quintuple layer intercalated, it's a 1610. If a 3-layer intercalated, 3-layer with BT, it forms a 1816 now. Then, so this this separation layer, BT separation layer, weaken the interlayer antiferromagnetic coupling and enhance the interlayer ferromagnetic coupling. The meaning this heterostructure compound should involve competition between interlayer antiferromagnetic and the interlayer ferromagnetic coupling now. So indeed, for this member with M=3, the ferromagnetic phase is already experimentally observed now. And this is a theoretical calculation showed, in the for these two members, M=1, 2, the ground state still has a lower energy as compared to ferromagnetic. It's supposed to be antiferromagnetic, but the energy difference between AFM and FM is not very large. So maybe it's tunable though. So this is what I'm going to show you now. So these heterostructure compound, as I just stated, they can also realize a range of topological state, including axion insulator and high order TI. So if a system could have this heterostructure compound can show out of plane ferromagnetism, it can show such a whole high order TI with 3 pair of chiral hinge state as shown in this schematic. If they are reduced to a 2D thin layer, they can show variable variety of the topological state, including a high temperature quantum anomalous Hall, quantum spin Hall, and so on. And experimentally, this system has been studied. 147 is reported to be AFM-TI. 1610, there are several papers. Some people reported it's also AFM-TI or axion insulator. Yeah, FM, the 1813 is reported to be ferromagnetic axion insulator. So next, I'm going to show you our work. So for 147, I just mentioned, previous work already showed this is AFM. This is AFM transition. On the field, it shows spin flop transition. Our passive measurement show it has a topological surface state and it's gapless. So the conclusion is AFM-TI. So we found that if this material is doped by a little bit antimony, 15%, it can show ferromagnetic phase. This is our data. So they show ferromagnetic transition. This heat capacitor also showed anomaly corresponding to this ferromagnetic transition. And also in the isothermal magnetization, we didn't observe the spin flop transition, which is expected for AFM ground state. So in collaboration with our user, Shilong Yang at the University of Chicago, his group also helped us did passive measurements. So we also in this ferromagnetic phase we also observed the topological surface state, which is also gapless. Yeah, he also did the circular dihorizon passive measurement. As you can see here, it's antisymmetric. The spectrum is antisymmetric. That is consistent with the helical. So surface state should have a helical spin texture. So this work is already published last year. And then my student, Yingdong Guan, together with Sam, did a very systematic study. So now we have established the phase diagram for this 147 alloy phase. So from this is magnetic phase diagram, you can see the ferromagnetic phase exists in wide composition range. And and also you see the AFM phase can recover at high concentration of antimony, so it has a double transition. First ferromagnetic, and then followed by the AFM. So that's strange. One interesting phenomenon we observed in this phase diagram is that so the interlayer coupling is dependent on carrier density. The reason why we see AFM is because at this concentration, the carrier density is minimum. It's 2 orders of magnitude lower than that of parent compound. So it looks like interlayer ferromagnetic coupling requires a certain level of carrier density. Meaning interlayer coupling, ferromagnetic coupling may be mediated by IKKY interaction. And we also found the antimony concentration tuned carrier type from electron to hole, and at this concentration near 30%, the Fermi level close to charge neutral point. So this system showed a lot of exotic phenomena. So I will not discuss those. This data has not been published yet, but we will present it at much meeting. So next I'm going to show you the tuning of magnetism in 1610 phase. So for this composition, we can make both AFM and FM phase. So this is AFM sample. You see the magnetism substitution show a sharp peak that corresponding to antiferromagnetic transition. Yeah, this sample also has same composition, but show ferromagnetic transition now. So this sample were prepared in with slight different conditions. Here, this diagram show the growth condition. So the difference in growth condition is very small. So the major difference is the growth temperature window. For FM phase, is grown in the window from 595 degree to 580 degrees. So the crystal is grown in this temperature range, and the quenching temperature is at 580. And for FM phase, it's grown from 590 to 575 and quenched at 75. So the difference is not really large, but they generate very different magnetic phase. One is AFM, the other is FM now. So and our systematic work showed, this the switching of magnetic phase, basically is due to the difference in manganese vacancy and the manganese anti-side defects. So we found high density manganese vacancy and manganese anti-side defects favors ferromagnetic phase. This is revealed from the TEM study. So the work, this work done by Lei Qin on the guidance of Nassim. So they compared atomic image between AFM and FM phase. So in FM phase, the data shows it has a lot of manganese vacancy on manganese layer. So those red dots in this imaging represents manganese vacancy. So in the sample with AFM phase, so the manganese vacancy is much less. And this we can understand why the high density manganese vacancy can favor FM phase. This can be understood with simple Hamiltonian analysis. So the Xulong Yang did that, a very simple model. So if we have less manganese vacancy, then interlayer antiferromagnetic coupling will be stronger than the coupling between anti-side manganese and the manganese layer. So HIL larger than HD. In this case, the AFM phase would be favored. But if we have too many vacancy on manganese layer, this coupling strength becomes smaller, could be smaller than HD. HD is the coupling between anti-side manganese and the manganese layer. So then it favors AFM phase. So this work is already published in recently in later. And Shilong Yang at the University of Chicago also did RPAS measurement on both phases. So in the ferromagnetic phase, they found the ferromagnetic O-ring open the gap on the surface state. This observed in MnBi2Te termination layer. So here I show you the density, the energy dependence of the intensity. So at the Fermi level, you can see from paramagnetic state to the ferromagnetic state, there is a density loss, intensity loss, meaning gap opens. So gap magnitude is about 15 MeV. And in BT layer, there is no gap opening observed. In AFM phase, and it's still gapless. So looks like the AFM phase is critical to open the gap. Okay, and so our in-house research has also attracted a number of user projects. So some of them already get very good results. Here I want to mention some of them. So one is time-resolved RPAS measurement on a 147 phase, MnBi2Te3 phase, done by Shilong Yang at University of Chicago. So through this measurement, they solved a long-standing problem. So why the topological surface state in MnBi2Te family is gapless? That has been puzzled for a long time. So their time-resolved RPAS measurement found a surprising wave function relocation of topological surface state from top magnetic layer into the buried second layer, as shown here. So basically, the topological surface state measured in RPAS is from the buried layer, not directly from the top layer. Top layer just generate rush bar band. That's also observed in the RPAS spectrum. So this is very important results. This work will appear in Nature Physics very soon. The other work I want to mention is the work done by Kang Wang at UCLA. So they did quantum transport measurement on nano device. They observed the tunable chain state in very thick films up to 21 subtopo layers. They still can observe the Hall resistivity quantization. They also found the Hall conductivity quantization is coupled to Weyl node separation. Yeah, but when it's thick, very thick, we still have a bulk Weyl state, but they still can observe Hall conductive quantization. The important conclusion they draw from this work is the interplay of chain insulator state at zero field and lambda level quantization at high field gives rise to intriguing anomalous lambda levels. So this is an important result. Yeah, the theory part was done by Alan McDonough at UC Austin. So this work was submitted to Nature Communication. Now it's under review. And also want to mention two work done by Venka Goplin's group. It's an internal user. Yeah, they did two pieces of nice work. One is magneto-photonic coupling in MnBi2Te. That work is already published in Nature Com last year. The other work is the exchange coupling between localized spin and topological band. So this work is recently published in advanced material. So and finally, I put up the summary. So here is the major conclusion we can draw from the work I presented above. So first, we have demonstrated idea type 2 Weyl semimetal state in MnBi2Te through an antimony doping. So we observed, electronic structure transition driven by AFM to FM transition, and we also observed the remarkable transport signature of Weyl state, including chiral anomaly effect and a large intrinsic anomalous Hall effect. So now also we studied the magnetism tuning in both a 147 and a 1610 system. I hope we can find more exotic quantum state in those systems. Yeah, that's all I want to present. Thank you.